So now we've got this disk method for finding the volume of solids of revolution. I want to look at a few examples, right? See how we can use this to get some actual numeric volumes. So to start with, I want to think about the volume of the solid generated by revolving the graph of y equals x cubed. That looks pretty steep graph here. That looks like this. And I want to revolve it around the y-axis. Okay. And I'm going to do this from y equals 0 up to y equals 8. And if we do that, you kind of visualize here what this is going to look like. It's going to have this kind of shape. Right? It's going to be, and I don't want to really draw this. I don't want you to think I'm drawing the function over here, right? Because obviously the graph goes below the x-axis over there. Um, I'm just kind of trying to sketch out the solid so we have some idea what we're looking at. Looks kind of like a really narrow, steep sort of cup. Okay, so how are we going to do this? Well, I'm doing this with respect to the y-axis. And one thing I really want you to take away from this whole chapter, there's nothing magical about the x-axis, right? Pretty much all of the stuff that we can do, at least in this chapter with respect to volumes and such, with respect to the x-axis, we can also do with respect to the y-axis just by switching the variables. Right, so if we're doing this with respect to the x-axis using our disk formula that we got in the last lecture, that was our formula. Well, if we're doing this with respect to the y-axis, it really is the same thing. It's just going to be with respect to y instead of x. And those a and b's up here, the a and b's are x values, and down here, they're going to be y values. All right, we were given two y values, right? We were given 0 and 8. Excuse me, forgot to square the function here. Right, square and square. All right, so my formula here is going to be pi times the integral from 0 to 8 of something dy. All right, well to get that something, I've got this formula here. I know what the function that defines the curve is. I just need to solve this for x instead of y. Right? So if y is equal to x cubed, then x is equal to the cube root of y, which is y to the 1/3. So I'm going to put that in here. And now we're more or less home free, right? I can use my power rule here. This is pi times 1/3 plus 1, that's 4/3. And it's going to be divided by 4/3. So this will be times 3/4 y to the 4/3 evaluated from 0 to 8. All right, so put these numbers in. This is 3 pi over 4 times 8 to the 4/3 minus 0 to the 4/3. What's 8 to the 4/3? The cube root of 8 is 2, and 2 to the 4th is 16. So this is 3 pi over 4 times 16, which is 12 pi. Yep, there's my answer. Right, there's the volume of this solid of revolution calculated using the disk method. So this question is another one of those from what we already know sort of questions. I want to derive the formula for the volume of a sphere of radius r. If you flash back to your high school geometry class, the volume of a sphere is 4/3 pi r cubed. So this is where we want to end up. Now we're thinking about doing this using the disk method, right? So I want to define this curve here that when we rotate it, we get this solid of revolution. We get a sphere. Okay, well this curve here is a circle whose radius is r. And the formula for the radius of a circle, the formula for a circle whose radius is r, is x squared plus y squared equals r squared. All right, so now let's get our formula here, right? Our formula for the volume is pi times the integral from a to b of y squared dx. Yeah, I know we usually put f of x there, right? I put y squared there for a reason. All right, so bear with me for just a second and you'll see why. So what I need to do is I need to take this formula over here and solve it for y, just like we solved for x in the previous example. Well, if I do that, I'm going to subtract the x squared. So y squared equals r squared minus x squared. Now you see why I wanted to kind of leave the y squared alone, right? Y squared is r squared minus x squared. So this is pi integral r squared minus x squared dx. Now, if you didn't see that and you went all the way and solved for y, that's fine. You'd have gotten y is equal to the square root of r squared minus x squared. And when you squared it up here, the square root would have gone away. You'd end up in the same place. So what are our bounds? Well, I want to get the whole circle, so I'm going to go from negative r over to positive r. All right, so let's do the integration. This is pi. Now be careful here. Remember, r is a constant. So this is r squared x minus x cubed over 3 from negative r to r. Now let's put these variables in here. This is pi r squared times r minus r squared over 3 minus negative r squared, excuse me, it's just r squared times negative r minus negative r cubed over 3. And this is a pain, right? Lots of negatives floating around, lots of parentheses. All right, so let's just clean it up. This is pi times r cubed minus r squared over 3. All right, so this is going to be minus r squared. The negative outside makes it r cubed. The negative outside makes it positive, so that's plus r cubed. Okay, this is minus r cubed over 3. This minus makes it positive. This minus makes it negative again. So this is minus r cubed, excuse me, that's a cubed over 3. And this is also a cubed here. And this should be r cubed. All right, combine some like terms. This is 2r cubed minus 2r cubed over 3. Do a common denominator, 2r cubed. That's 6r cubed over 3. When you subtract 2, look at that, you get 4/3 pi r cubed, exactly the formula we expected. So, just like in the last lecture, right, when we derived the formula for the volume of a cone, and you finally got to kind of see where the 1/3 comes from, same thing here. Right, now, if back in your high school class, that 4/3 appeared to just kind of come out of nowhere, this is where it comes from. So I've got one more example here, and I picked this to illustrate a specific interesting kind of property of our approach with this disk method. So I want to find the volume generated by revolving the cosine of x. I'm not doing this in any particular scale. I just want to get a quick sketch here. From x equals 0 to x equals 2 pi, so a full period. Right, and we're going to rotate this, so we're going to get this part down here and a very similar part over here. So we're going to kind of have 3 sections here, right? The left, the right, and the middle. And all I'm going to do is I'm going to apply my formula. Right? That's it. Nothing crazy. Right? I have the formula for the boundary of the region. I'm going to revolve it. My formula says volume is equal to the integral from 0 to 2 pi of y squared. So that's cosine squared x dx. And we know how to do this. This is the integral from 0 to 2 pi